Hello again. Let's now go further with our sampling ideas. So now we're looking at the sampling distribution of sampling mean, or sample mean. There seems to be too many words here, but the basic idea here is that the distribution here depends on my sampling scheme. That's why it's the sampling distribution. If I change the way I sample, then my distribution will change as well. So, basic ideas, in any situation, population mean mu is unknown, and the natural way to estimate this is to use my sample mean x bar. And inference, meaning decisions about mu, whether it's changed or is the same as before, will require the distribution of the sample mean x bar. And the distribution of this x bar depends on population distribution and the sampling scheme. And that's why it's called the sampling distribution of the sample mean. Also, sigma squared will come in there somewhere as well. And the results as to exactly what distribution I use in the end will depend on whether the sigma squared is known or unknown. And of course, usually it's not known here. So we'll take a look at these three cases below. The first idea is this. If sigma is known, I know that if I start with normal things, if everything is normal, then the x bar, which is just simply a sum, and then divided by n here, some scale factor, is also going to be normal. We know the mean of x bar is mu, and the variance is sigma squared upon n. It's easier if I look at the standardized version. So if I standardize this, it's x bar minus mu over sigma. So if it's standardized as usual, then here the mean of x bar is mu, we subtract that, and the standard deviation is the square root of this sigma squared upon n, so it's going to be sigma on root n. And so you might often see this expression here, and this is the one we'll be using all the time. The standardized version of this is x bar minus mu over sigma on root n, and that's normal not 1. So here we're assuming everything is normal, and the variance is known. And so as we saw in the histograms earlier, the same result actually seem to hold. As an example, it takes on average 150 seconds to serve a customer with a variance of 900 seconds squared. Probably that a random sample of 25 customers will have a mean service time greater than 160 seconds. So I'm looking at a sample mean time, of course, and that word is missing. I should put that in there just to be consistent and careful. So I'm looking at here, x bar here is my sample mean, and that will have a normal distribution. The sample mean here, well, the mean here is 150 seconds, so that will stay as 150. And the variance here is my sigma squared upon n idea. So sigma squared here is 900, and the sample size n is 25. What I'm looking for is probability that my 25 customers will have an average service time bigger than 160 seconds. So that's the same as in the usual way I standardize, that's bigger than 160. The mean here is 150. And the standard deviation is the square root of this. So the square root of 900 on 25. So this comes to, I can calculate that using R as before. So the 160 minus 150 is 10, divided by square root of, and I had 900 divided by 25. That comes to 1.67. And this time I'll use R for this, just to illustrate how R works. There's my R commander. I got distributions, and I want continuous, and that gives me normal. And I want probabilities. So the variable value is 1.67. And I wanted, in this case, I'm looking at probability of being bigger than. So it's the upper tail. Okay. And I get 0.0474. quite a small probability, about 5% or so. Part 2 says, I'll do the same but with 100 customers now. So now my X bar is still normal. The mean still stays as it was before, 150 seconds. The variance is sigma squared upon n 900 over 100. I have a probability that X bar is bigger than 160. Same as probability that Z is bigger than 160 minus 150. And this of course works out to be 9, so I want the square root of 9 over here. That's probability of Z being bigger than, there's 10 over root 9 is 3, so it's 3.33. So again I'll use R for that. .33 upper tail, okay, 0.0004. This time is less than 1%, much less than 1%. So you can see the effect of sample size on this. Going from 25 to 100, the probability has become very much smaller. The distribution becomes much narrower very fast. Some examples here says probability sample size 100 is drawn from normal mu 16. I don't know mu in this case. Find X bar less than mu. Well, this is simple if you understand what's going on here. I know that X bar is going to be a normal distribution. The mean of X bar is the same as the mean here, mu. And the variance is 16 over 100. Probability X bar is less than mu. Well, mu is the mean, right? So X bar is symmetric around the mean. There's mu. So that should be simply 0.5. But you can work it out if you wish, because if I go further here, that becomes Z is less than mu minus the mean, which is mu over 16 on 100 if you wish. Take the square root of that. That simply is probability of Z less than 0, and we know that Z is symmetric around 0.5, below 0.5 up. But I can see very clearly, because X bar has mean mu, being below mean will be exactly 0.5. This one here, X bar minus mu less than 0.2, so I'm looking at the distance between X bar and mu. So I know X bar has this distribution that I've listed there earlier. This is the same as saying, if I go slow here, X bar minus mu, I divide by the standard deviation, 16 on root 100 square root of. Is less than, I divide this side by the same thing. Now, of course, the X bar minus mu on this thing should be Z, but it's actually the absolute value of Z. So again, X bar minus mu over the standard deviation. The standard deviation of X bar is the square root of this. Absolute value of Z is less than, now there's 16 on 100, the root of 16 is 4 and the root of 100 is 10, so it's 0.4 there. This comes to 0.5, you can calculate that out if you wish. So I'm looking here at the probability in the normal node 1 distribution, in the middle between 0.5 and negative 0.5 over here. So the table gives me this value there, which I can look up, 0.5, and here's my table. 0.5 is 0.1915, so I can double that. So I get 0, and I get 3, 8, 3. There it is. Now, slightly different. The same idea as before. x bar minus mu less than k is 0.95. So I take a look at this x bar minus mu, absolute value, less than k is 0.95. So I know how it will work. I divide both sides by the standard deviation, so it's k on 16 on 100 square root of, and that's equal to 0.95. So, well, I know how it works. I'm looking here at 0.95 in the middle. So the tail probabilities add to 0.05, and that's 25%, 0.25 in this tail. The same here. Gives me 0.95 in the middle, and so I know I'm looking at critical values of the Z distribution. Critical values at the bottom over here. I want 0.025 in the tail, 1.96 again. That value, 1.96. So this is 1.96. In other words, I want k over 16 on a root, 1600 square root of to be equal to 1.96. And so 16 on root 100, essentially that's 4 on 10, that's 0.4. So k is 1.96 times 0.4. Use R for that. 1.96 times 0.4, and that comes to 0.784. So some of these ideas we'll be using again in the next chapter on estimation. Second case, population is normal but sigma is unknown. So what happens here is I'll replace my sigma by my sample standard deviation S. And so previously I had here x bar minus mu on sigma on root n. But now that sigma has been changed to an S. And that changes the distribution to a t distribution. A little bit subtle here, but changing the S to sigma to S changes the distribution. So it's a t distribution, and the t distribution comes with degrees of freedom. Now we saw earlier the chi-squared distribution also came with degrees of freedom. This is similar in the sense. It has a degrees of freedom as its parameter. So what does the t distribution look like? Well, here, before we get to that, first of all, S squared is the sample variance as before, and it is an estimator for the population variance. Now, if you look at what this works out here is, I'm dividing here by n minus 1, and this is the degrees of freedom that I'm getting for my t distribution. That's always the case. Whatever I divide here by to get my estimate of variance will be the degrees of freedom for the corresponding t distribution. Whatever situation we look at, you'll find this is consistent. The second thing is that the variance of x bar is actually sigma squared upon n, or the standard deviation of x bar is sigma on root n. We estimate this by s on root n, sample standard deviation root n. This is called the standard error of the mean. Words you'll see later on as well. Now the t distribution looks very much like the normal distribution. So here is a comparison of normal with t. So the black one here, first of all, is normal. And then the red one here is t with 1 degree of freedom, and then the green is t with 2 degrees of freedom. You can see that the t is a little bit lower and flatter. If you look at various t distributions, you'll find again, as we increase the degrees of freedom, it becomes higher and higher. In fact, as t becomes very large, it becomes very much closer to normal distribution. So if you look at some values of tables for t distributions, you'll find, because it is every t distribution comes with its degrees of freedom. Once I have here t with a degree of freedom, that looks like a normal curve. If I have another one, then t, say, take a look at t 100, then it'll look a bit like this. That's t 100. Now, I can't list tables of this kind for every degree of freedom for t, because that's a very large book, but I can list the critical values. So what you'll find here is the t distributions list only critical values, and that's usually all we're interested in. Of course, R or whatever other software packages will give you all probabilities you require for any distribution, any t distribution, but here the ones I'm interested in really are the tail critical values. So probability here of 0.05, for example, and then this is, say, T9. So I look up degrees of freedom here is T9. 0.05, the value here is 1.8331. And so the use of the t-value is mainly to do with looking at these critical values, not so much calculation probabilities. If I then, and you can do this yourself, if I look at critical values of the t distribution, if I'm looking at one, this is looking at degrees of freedom 1, 9, 60, and so on, the notation I'm using over here is that bit here is the degrees of freedom, and that bit here is the probability I'm looking at, critical probability over here. So at 0.05 level, if I'm looking at 1 degree of freedom, look at the tables, 1 degree of freedom, 0.05 level, the value is 6.3138. 6.3138. If I look at the same for 0.025, 1 degree of freedom, 0.025 is 12.7062. Of course, it's expected, because essentially what I've done is I've looked at a t distribution, T1. If I look at a probability here of 0.025, 0.05 will be here somewhere, yeah? So the value for t here will be larger than it will be over here. Likewise, for 9, you can look up the values yourself. I get 1.8331 for t 9.05, and for 0.025 I get 2.262. And so on. You find as we get to the larger values of the degrees of freedom, the value actually becomes closer and closer, or the changes become smaller and smaller. The infinity values here, 1.6449 and 1.960, in fact are the same as the z values, or the normal node 1 values. So at infinity, t and normal node 1 are exactly the same. So the values you'll find for t infinity over here are the same as the values you'll find for the z distribution, critical values at the bottom here, exactly the same. 0.05 is 1.645, 0.05 is 1.645, 449 if you wish, 0.025 is 1.96, 1.96, and so on and so forth. So the t distribution becomes the normal distribution for very large degrees of freedom. The last case here is when I've got population that's not normal. We don't really care exactly what happens here as far as whether we know sigma or not in this case. So the way it works is that we've got an arbitrary distribution, and we can actually use simulations to guide us here. So you can use what's called, and I can see that I don't have this available here, the actual URL, but you'll find the RISE lab has simulators you can use, and you probably can see this in your, we might show this in lectures if you've got time. So what I've got here is, in the top panel I've got the distribution I'm going to simulate from, and then the third panel shows the sample means of 1,000 samples of size 25, and the last one actually is the same but with a normal curve on top. So here are the results. Have a look. This is the this distribution I was simulating from. It looks nothing like normal. But the sample means, I've got 1,000 sample means here of size 25, is very much closer to normal. In fact, the normal curve on top of that looks almost like it's normal. So that's the basic idea of how this works. So we can formalize this in this very important result. If I've got an arbitrary distribution of some kind, and I take a look at a sample mean, the standardized sample mean is approximately normal not 1. Now I actually have used sigma over here, but often of course we don't know sigma, and I'll replace that by S1. The first thing is, what it says here in the theorem is, for large enough n. The large enough is not quite well defined here, but you'll find for most applications n equals 30 or larger guarantees almost that you get a very good normal approximation here. If sigma is unknown, then I must replace it by this samples in the direction S. When I do that, I get a t distribution. So whenever I replace sigma by S, I get t. Now, of course, if t has a large degree of freedom, it becomes very close to normal anyway. But you'll find that most often we'll use t, and t is the standard or the default that's used by all software. This is the most common situation. As an example, I've got a particular long life light bulb has a mean life of 1500 hours with a standard deviation of 300 hours. So I know this is my sigma. I want the probability a random sample of 200 bulbs has a mean life less than 1450 hours. So my x bar here is approximately normal. Approximation because of CLT. And the mean here should be 1500. And the variance here should be sigma squared upon n. So that's 300 squared over 200. I want probability that x bar is less than 1450. So that's the same as probability that z is less than 1450 minus 1500 on the square root of sigma on root n, sigma on 200. So here's my sigma on root n. Or I can simply put the square root of the whole thing, the 300 on 200, that comes to the same thing here. And here I can use again R for calculations. So the top line here is 50, negative 50. Negative 2.36. And if I get probabilities from R again, distributions. So I want here negative 2.36, and in this case I want a lower tail probability. And I get 0.0091. Not very often will I get that. The sample mean has a value less than 1450. Okay, so that finishes our sample mean. We'll finish off also proportion in this lecture, and then we'll take a look at a summary. So the first part here is looking at proportion of voters as an example who will vote Liberal at the next federal election. So you ask a random sample of n voters, and here, so n, in this case, we've got a sample of size n, and we model that as identical Bernoulli trials, where p here is the probability that somebody will vote for the government, vote Liberal, and it's population proportion here. We're looking at population proportion of voters who will vote Liberal at the next election. So my x1 to xn here are my IID trials, independent and identically distributed, xi is 0 if I don't vote Liberal, and it's 1 if I do vote Liberal. So xi actually counts the successes in this case. If I take a look at my earlier results, then I know that for the Bernoulli, the mean is just p, and the variance is p times 1 take p. If I put x as the sum, then x is the number of successes in n ID Bernoulli trials. X is binomial now, and we know that E of x, the mean is np and variance is np, 1 take p. That's to set the whole thing up. Now, population proportion is x over n, the number of people who will vote Liberal over the total number. That's 1 over n times x i's added up. This is the same as x bar, population. This is the sample mean, x bar. So proportion actually is also a mean of some kind. It's a sample mean. So all the results I had for sample means follows. In particular, got my sigma squared there. In particular, the mean of p hat is the same as the mean of x bar, which is p. I had that earlier. The variance is that you're going to be sigma squared upon n. Sigma squared is p, 1 take p over n in the previous slide. It's my sigma squared, and there's my mu. And in particular, z, which is the standardized mean here, x bar minus e of x bar over the square root, well, sigma square root of n is going to be n normal, not 1, approximately normal. So this is the main result. My p hat, which essentially is my x over n, proportion in the sample, minus its mean, which is p, over the variance, standard deviation, p, 1 take p on n square root of. This standardized thing quantity has a distribution that is approximately normal, not 1. And of course, as we said earlier, sample size of n bigger than or equal to 30 gives us an excellent approximation. Example here says that in the last state election, Labour received 55.5% of the votes. A poll of 500 voters is now taken to determine if the government has declined in popularity since the last election, and this proportion gives us 53%. So I know here I've got 500 voters, and my p hat here is 53%, my sample proportion. What is the probability that the sample proportion is 53% or less, assuming the government support remains the same as at the election? So here, p is 0.555, the proportion of voters who voted the government, and my standardized sample proportion z is this much here. So I'm asking whether p hat is less than 0.53, essentially given p is still, so 0.555. I standardize both sides, and then I get 0.53 minus my proportion, which is 0.555, over p, one minus p, on root n, and I had a sample of size 500. Square root of so I can work out the value here from R as before. So let's do that. 0.53 minus 0.555 over square root of 0.555 times 0.445 divided by 500. I get negative 1.12, 12486. So I'm looking at distributions again, continuous, normal, probabilities. So the value here I'm going to get is negative 1.12486. And in this case, I'm looking at the lower tail, so it's okay. And I get 0.1303. negative 1.212486. About 13% of the time I'll get that the sample proportion is less than 53%, even if the government is staying at the same popularity. So here a sample of 500 gave me a decline, if you like, in the sample itself of a bit more than 2%, 2.5%. But that's still within what we call sampling error. In other words, my sample contains error, and I've quantified the error in this case. And so this decline isn't real. It's part of my sampling error in one sense. In other words, population proportion of voters can still remain 55.5%, but my sample can have some variation, and this is within that variation. So in fact, I've done the work over there. So summary here is the most important part. Just some words. Population is modeled by some random variable. A sample is an IID set of random variables that are from the same distribution as population distribution. The sample mean is as before. It's just the average of the values. The mean of the sample mean, E of x bar is mu, and the variance of x bar is sigma squared upon n. The important part is this slide over here. It has all information about distributions. The most popular situation is going to be where sigma is unknown, and we have this situation. You can see in each case I'm using the t-distribution. In the first case, because I've got an exact normal population here, in the first case it's normal to start off with, this is an exact distribution. In the second case it's approximate, but it's still t. So you can see that the t-distribution is the most often used distribution over here. Regarding proportions, we use the normal here because here the p is known to us and p is part of the standard deviation of variance. So a similar result over here. This slide contains everything you require to know in the end, barring the ideas of sampling and the problems of sampling we saw earlier. Thank you. That's enough for today.